Our next speaker is Kevin Shaw from Sensor Platforms. As I mentioned this morning, Sensor Platforms deals with signals from inertial sensors and extracting useful information from that. And Kevin's going to explain to us how that works and how combining information from inertial sensors with vision can yield better results than just image data by itself.
Sounds great.
Thanks for being here, Kevin.
And, all right. Well, thank you very much. My name's Kevin Shaw. I'm Chief Technology Officer at Sensor Platforms. And I want to spend the next half hour or so talking about visual systems and inertial systems and how the two of them can work together to solve a broad range of problems. First off, I'd like to motivate the conversation and take a look at the markets that are served by this. First off, we've seen the use of vision systems in games. Well, mobile platforms more than anything. It is a remarkable state of affairs that we have smartphones, small little phones, that basically have the computational power of what was a supercomputer a decade or two ago. They have the battery, CPU, graphic processing unit, and, a high-def camera that'll go in with it. This is what we're seeing in computer games now. They've done amazing things, but I think there's more that these can do from a gaming perspective. And then there's augmented reality that is being serviced by computer vision.
It is. Okay, great.
This has also been very hyped in the past several years, but it hasn't really taken off yet. I was looking at some of the examples at AWE earlier in the week, and I'm still seeing images that bounce around and that jump around. I still haven't seen the level of accuracy that I'd like to see. And then there's indoor navigation. There's a lot of companies and a lot of technology trying to service the indoor navigation market, and vision could be part of it. Why not? I'm standing here walking around here. I'm not bumping into things. I'm using a computer vision system. Oh, sorry, human vision system. It works quite well. Why could that not be part of the indoor navigation solution? Well, it's tricky. And I will go into some of the reasons why it hasn't so far. Oh, and of course, power. Power is a major one of them. How do we solve an always-on computer vision problem? I'll hint a little bit at hyperphotography, which is the ability to get more information into a computer or into an image than is actually there. And robotics. It goes without saying that most of the terms we're going to hear in the computer vision world come from the robotics world. A lot of the development was done there for a very simple reason. If I wanted to have a mobile camera going through a field, I probably had to have a car battery sitting next to it and a wheeled system and a computer on it. Back when most of this stuff was done, they were quite heavy, and then you needed the large platform. And so we'll talk a little bit about visual odometry. All of these are drivers for the vision system market. Also, you can go into things like computer construction equipment, where you want to have perimeter safety, identify people around you. All of these are needs for a strong and stable vision system. I also want to touch on context awareness. We saw that in actually just the presentation a moment ago. Allowing a computer system, a handheld system, to understand not just the world around you, but what you are doing. What am I doing? In the Samsung Smart Stay, for example, identifies whether you're looking at it, and when you turn away, it stops your movie or dims the display. Vision systems can be used for a contextual understanding of the user themselves. And then there's the critical shift here. We hinted at the robotics and then the shift to the mobile here, but also the shift to the wearables. And I'll address this a little bit more in just a moment. But this is a very important one. And then natural interfaces. I interface with the world. Most of the information that I bring in, yes, I listen, but I also see. And this is such a natural way of viewing the world that I have to ask the question of why don't mobile devices see the world and feed me information in the same way? The example that's given here of identifying a medicine bottle in front of me. This is sort of a natural state of where the information comes in, not just of understanding the walls around me, but understanding what I am interacting with and feeding me additional information. So let's move forward here. I mentioned that robots were a really good starting point for this. When you had something heavy like this and needed a car battery to run the processing system, it made good sense. Yet here we are. We have smartphones now. What's in those? Well, basically a supercomputer. I've got a quad-core, octa-core processors couple of GPUs, quite a few, frankly. Great screen, I got a battery, HD cameras on both sides. So why aren't I doing more computer vision with them? Let me ask you a question. For anybody that's not texting right now, where's your phone? In your pocket, perhaps? Tell me what the camera is able to do there. Not much. All this phenomenal processing power, and it's in a holster. Big deal. Oh, what do we have here? Google Glass. I think this is going to be a phenomenal change in this, and this is probably obvious to most of you in the room. When I can put a camera up here, oh, and it's on an optically stabilized platform. My head is stabilized by a closed-loop feedback control system with my eyes. The reason it's so stable is it's held that way by a closed-loop feedback system. That's a great place to put a camera. When this starts to happen, the computer vision world will take off and will provide tremendous value for it. This is the time now. Yes, Google Glass is a little bit early, and yes, there's going to be plenty of deprecating remarks about people wearing it, but it is the start. So the challenges that we need to solve here. Vision systems, you all probably know a fair bit. It's always difficult talking to an audience. I'm not quite sure what everybody knows here. I come from an inertial background myself. So I'll address some of the limitations into a vision system. Typically, vision systems are monocular. Yes, it'd be nice to be able to do binocular like we as humans have, but it's just half the processing power, half the cost to be able to do a single camera lens. But they come with some constraints. One of which is lack of metric scale. If I take this picture from a dollhouse and hand it to a vision system, will it know it's a dollhouse or a real kitchen? Well, if it's a monocular system and lacking a priori knowledge of the scene, it won't know. It's just a scene. Vision systems, monocular vision systems, don't know size. I need to provide it dimensional information in order to understand the scene. Where will I provide that information? Well, we'll talk about that. Next is pose stability, and we'll talk about pose. Pose is the combination position plus attitude. Pose stability is an issue. If I'm tracking feature points, and even feature point stability is an issue. If I'm tracking these, trying to identify my attitude and position, if I have feature points that either move, get lost, I can lose my pose. There must be some other ways to be able to resolve and stabilize that system. And next, there's power. Google Glass is a phenomenal, capable platform. But if I run the processor at full out, I'll drain the battery in 7 minutes. I can't run a full-on vision system running thousands of feature points on that platform. Someday, maybe, but we're going to have to find some other tricks to solve this problem. So where do I find my sensors? Anybody have a smartphone? Most people don't realize there are about 20 sensors on most smartphones these days. This is actually what my company specializes in. Sensor Platforms does sensor algorithms embedded largely for mobile and wearable platforms like this. Some of these sensors are going to be critical for our conversation over the next half hour. In particular, those ones in the upper left, the so-called inertial sensors. The inertial sensors, and actually only 2 of them are inertial, but the other 2 just sort of always tag along. The inertial sensors are the accelerometer and the gyroscope, as well as the magnetometer, which tells you Earth north, and the barometer, which tells you altitude. This is what's called the 10-axis sensor fusion system. And what it resolves is a quaternion or attitude or yaw, pitch, and roll. Now we can, oh, yes, I have to put in my gratuitous MEMS slide. I have a background in MEMS, and part of the reason that we're able to take these little tiny sensors and make them is simply because of the ability to use and build silicon devices like this. The reason MEMS have gotten so small is it really is taking mechanical design properties and leveraging the semiconductor design tools that's already being used for the CMOS that a lot of these vision systems are running on. If I have tools for 28 and then 22 nanometer capability, I can actually draw phenomenally precise mechanical structures. Bosch would probably be unhappy at me for showing such an antiquated device as those accelerometers up there. 2 millimeter by 2 millimeter is quite old at this point. The new ones are 1.2 millimeters by 1.5. They continue to shrink. And at that point, they're small enough, low enough power to go just about everywhere. So let's go through the 4 major sensors very quickly and give you an idea what information they provide and how they can help solve the vision problem. First off is the accelerometer. I bet you have a good idea what it measures. Actually, you'll find it surprisingly tricky what it actually does provide. An accelerometer basically measures linear inertia. Inertia is another way of it's described very well by mass. If you've been in an elevator, I'm sure you all have, when you feel the elevator go up, you feel your weight sort of pull you down a little bit. The frame or platform of the elevator is much like the accelerometer. As it goes up, you lag behind a little bit as you absorb the energy and absorb the kinetic energy. Same thing in an accelerometer. I have a mass attached to a spring, and when I shove the frame here, the mass lags a little bit in the inertial frame, and I get a displacement. Pulls back a little bit. Turns out that displacement is exactly proportional to the acceleration applied to the frame. Okay, I just need to measure displacement. Anybody good at measuring displacements? Well, it turns out that those frames that we're seeing here, these are capacitive comb fingers here, are capable of measuring sub-angstrom displacements. I have a nice picture of a hydrogen atom there. We actually can measure 10th angstrom displacements, actually 100th angstrom displacements using these capacitive systems. There's an example of one up there. So what's it do for me? Well, first of all, it's really good at measuring acceleration, well, with caveats. It's really good at measuring vibration. Does anybody have a Fitbit activity monitor on your wrist? They're using accelerometers for most of that information. And there's 2 reasons for it. One, it's really good at getting motions, walking and whatnot. It's also very low power. I can run this thing continuously. It only takes 10 microamps. I usually wear my Misfit. That lasts for 4 to 6 months on 1 battery charge with continuous measurement of the accelerometer. This is the sort of low power we can run it at. And it's also very good at getting tilt relative to Earth gravity and position. Dead reckoning and calculating position is what we're going to talk about shortly. Next is the magnetometer. The magnetometer tells me where Earth north is. I know everybody tells you that the gyroscope is the really cool part of the device, and yeah, okay, they're really neat to design. But I depend on the magnetometer to know where my actual Earth north reference is. That's what I'm going to get my attitude from. And it measures, if you all had a compass when you were a kid, you always held it flat. Well, that actually is measuring down, because you held it flat relative to down. And then it tells you north. Turns out the Earth fields are not actually flat along the surface of the Earth. I always thought they were as a kid. They actually dive down about 30 degrees here in San Jose. But the magnetometers are 3-dimensional, so I can measure that and compute that. And then we do have the gyroscope. Gyroscopes are very cool. They do neat things. But they don't measure angle, contrary to what many people have said. They actually measure angular rate, the rate at which angle changes. Which means if I want to get useful information out of it, say to get angle, I'm going to have to integrate it. All right, that doesn't sound like a problem. Is there anything wrong with integrating something? Well, we'll see in a moment. So I'm going to need to have a starting angle to allow me to get the difference in the change from relative to that. They also actually consume a fair bit of power, about 100 times more power than an accelerometer does, which is why you don't find them in the wrist activity monitors. 1, you don't need the information, and 2, it'll drain the battery too fast. And finally, a barometer. Barometers are interesting. They are capable of measuring the air pressure difference between here and here. It's kind of amazing that you can do that. And the best thing is they do it for 2 to 3 microamps, a pittance worth of power. That's why some of the activity monitors do have an accelerometer and a barometer for counting steps and floors. And so here you see an actual trace showing the air pressure difference between different floors as you go up and down in a building. So this is our sensor fusion. I'm going to take 3 axes of accelerometer data, 3 magnetometer, 3 gyro, and 1 of the barometer, and that will be my 10. Fuse that all together in a Kalman filter, and there I have attitude. And that's going to be the basis of my dead reckoning. So what is it good for? Well, odometry, of course. That's what you're going to say, right? I want to get pose. Odometry is the way of measuring my pose as I move through a scenario. Pose is position plus attitude, my orientation relative to my inertial frame, as shown by this robot here. Pose is usually made up of the position vector plus a quaternion. So this seems pretty easy. I get acceleration off my accelerometer. I get my attitude off my gyroscope. Just integrate each of those, and I should be able to get dead reckon my way all around this room. That sounds pretty easy. It's just integration, right? Is there anything wrong with integrating white noise? Well, here's a trace of a common consumer-grade accelerometer. This is an LIS331DLH. 60 seconds worth of data at 100 hertz, 473 passes. It's pretty flat. What happens if I integrate it? Well, it was zero mean when I started, and I think you'll agree that, to a large extent, it is zero mean at the end at 1 minute. Across 473 passes, it's definitely zero mean, but any given trace won't be zero mean. My standard deviation, my variance is increasing the longer that I integrate. This means if I take the device and bolt it to a table and measure its velocity will appear incorrectly to start to diverge over time. This is called random walk. Well, what happens if I integrate it again? Well, my position diverges further. My position error, starting with acceleration, diverges as time squared. The same thing's going to happen with my angular rate signal from my gyroscope. When I integrate that once, that will also diverge linearly. But I also have a second order term here, which means I actually have third order divergence on an integrated signal. This is part of the difficulty with dead reckoning. And it's why if you're in the military, you buy ring laser gyros and you buy $100,000 accelerometers. I don't get a $100,000 budget for my consumer smartphone that I carry with me. My accels cost 30 cents, and if I'm lucky, the gyros cost 80 cents. So we're going to have to find some constraints and some solutions to solve this problem. But are we done yet? Well, I actually have one other issue I've got to deal with, and that is gravity. Turns out accelerometers don't just measure acceleration. I hinted at that earlier. Unfortunately, well, depending on how you want to look at it, they measure gravity and acceleration. Gravity very helpfully holds me to the floor here. But if I start integrating my position just straight off gravity, it's going to look like I'm falling through the floor at free fall rates. I have to remove the gravity term before I can even start to integrate my dynamic acceleration. Okay, it's 9.8 meters per second squared. What's the problem? Well, as evidenced by that picture there, if I turn the device, gravity seems to move relative to the body frame. I have an issue where gravity is measured in the world frame, dynamic accelerations measured in the body frame. I need to have the attitude between the two of them before I can subtract gravity. This is an issue because gravity is relatively large. If I make a small mistake, that will leak through into my solution and seem to be an apparent acceleration. And I may start to integrate that up, as demonstrated here. The blue axis would be gravity. The red is what I actually measure with my accelerometer. This is the bane of the existence of anybody doing inertial navigation work. So this is pointless. Well, not really. Clever software, Kalman filters, and really good engineering allows you to do the following. This is some work that my company's done. We started walking at the green dot there with the GPS and was able to dead reckon, actually pedestrian dead reckon, our way using standard consumer sensors all the way through. And if you're really clever and apply the proper constraints, you actually can provide a very stable solution. It's just very tricky. This particular one was done with a Samsung Galaxy S3, straight out of the box, just off-the-shelf sensors. This is the sort of information that we're going to use to provide the dimensional constraint that solves the computer vision problem. So let's jump over to vision systems. Visual odometry. a better way of describing the fact that I want to be able to walk and use a vision system to track my position and attitude as I walk through a scene. It has to do with being able to track feature points, and I'm not going to go into that. There's a great example there of IKEA ad. Different positions allow me to better identify different features. I'd love to go into that. I had made the assumption that most of you probably knew more about feature points, that I didn't need to go into that. Vision systems, though. We hinted at this earlier. A monocular vision system has a number of constraints and limitations to it. Some of the limitations are, one, what I call a dollhouse problem. They don't understand scale. I will need a second piece of information to allow me to resolve this problem. Well, as hinted, inertial systems can provide that information. Another way to resolve it, you have a difficulty of mapping points between frames over time, as evidenced by this picture here. The solution is, given that feature points sometimes disappear, it's not very nice of them, but they do, is to solve it by not just doing 10 feature points or hundreds, but sometimes thousands. And the computational requirements for that are enormous. Cohesion over long time scales. If you're using a Kalman filter-based approach, you're usually comparing one frame to the next. Cohesion over long, multi-second, multi-minute makes it very difficult to be able to track the exact same feature point all the way through, especially with occlusion due to lighting and other objects in the way. Robustness in the face of darkness or low texture surfaces. We as humans handle it, but it's very hard for vision systems. Feature points disappear. And the ability to maintain vision lock. If I have a vision system and I do that, there's too much motion blur. All of my feature points have been lost. Cohesion is lost from the early set to the next set, even if I bring it back. And finally, the enormous computational load. Hundreds or thousands of feature points, and especially Kalman filter approaches, do not lend themselves well. We talked about what you can do with Google Glass. That 7 minutes is going to be great for 7 minutes. How do I make it last longer? Well, it turns out that if we take an inertial nav system, fuse it with a vision system, we get some significant advantages. First off, I can anticipate feature point location. If I know that my vision system has moved 30 degrees, do I know where my feature points are? Well, my inertial system told me it moved 30 degrees. I may not need to track all of the frames to get there. I can tell you pretty accurately where that feature point will be, and my search window to find it is significantly smaller. I can reduce the number of pixels to search for by orders of magnitude. I can also reduce the number of frames because I don't need to track 60 frames per second to get there. I have a stable attitude and position reference in between those. I may be able to go down to frames on the hertz level, or even less. Power reduction due to opportunistic frame rates. If I take a vision system and set it on the table, it's not moving. Do I still need 60 hertz frame feature point detection? No. My inertial system tells me it's not moving. Once I do this, I can then pick up the vision system again. These sorts of opportunistic efforts allow me to significantly reduce power. Oh, especially when spatial and motion diversity is low. And finally, there's vision systems can be turned on. Imagine a museum scenario. I walk through the museum using pedestrian dead reckoning. It tracks my position quite well through. But the moment that I get to a statue, it knows I'm in a statue, and the vision system can turn on, immediately do feature point lock onto the statue and the surrounds, and begin to give me the augmented reality overlay that I expect. I can start to do this sort of opportunistically between the two scenarios and intelligently. This allows me to do full vision systems in very limited batteries. We hinted at this earlier, the monocular vision problem. We as humans look at these two scenes and automatically identify the one's real, one's not. Well, one, we can do the texture reference. There's a difference in the look. Vision systems have a lot of trouble with this. And so determining metric scale is a critical problem. Other issues, position estimates, finding ways to determine the scale estimate. The simplest solution is to use humans do. We have our two eyes. We actually know the separation between the two eyes that allows us to solve the scale problem. If you close one eye and then try to walk your way around, you can get attitude from that. But I can quickly lose my depth perception, of course, but I also lose my scale factor. Reference objects. This is done to determine scale in the IKEA ads. I showed you earlier the ones with the overlying sofas in someone's room. They put the IKEA catalog down there. It's the reference that they get scale from. And from there, everything else in the room scales accordingly. That works well until you lose lock with that. Until I lose sight of the catalog, or if something blurs. How do I maintain vision lock beyond that? Location estimates work. GPS, though, is not available indoors. Mapped landmarks do work. If somebody, for example, were to identify the points in a corner of a room, and I can identify those points, I can do my metric scale off that. But inertial estimates are frankly so cheap and so easy. Everyone here that has a smartphone has a full set of inertial sensors on there. They really sort of come free at this point. Oh, and depth cameras are great as well. Getting Kinect and PrimeSense doing their full depth cameras. So how do we combine the two? I'm going to try not to get too much into mathematics. I promised Jeff I wouldn't do that. But I did tell him I'd do a state vector. So here is a vision system schematic. I'm going to have a world reference frame, and my effort is to determine the red line here. That's my pose, my position and attitude relative to the world frame. Within the IMU camera body, I'm going to have some separation between the IMU, the inertial measurement unit, and my camera. And my camera system is going to be looking at the world from across the blue vector. It sees feature points. My job is to map the feature point back to the world reference frame and the IMU, the red vector. Here is our challenge. So I need a state estimation system. Characteristically, this has been a Kalman filter. Now, Kalman filters are really interesting beasts. They were developed for Apollo. Let's argue that's one of the reasons we actually got to the moon. They're an excellent system for identifying, actually reasonably efficiently, identifying states. Here's an example of how I like to view a Kalman filter. A Kalman filter takes measurement information in from sensors, but it also has a model of the world that allows it, when the measurements don't work well, to continue operating. If you're driving down a freeway, for example, you're keeping in the center of your lane. You see the dots going along each side of your lane, and you just center within that. On 101, they're always doing work, and those dots often disappear. They repave the freeway and don't bother to put them back. Do you stop driving then and say, I can't go? No. Your brain actually is an excellent Kalman filter. It looks on and says, I know I need to be there. The cars here are going at the same speed. I can keep going. You have a model of a system for where you need to go relative to the freeway. You've lost some sensors, but you still have a model. When you see the dots on the road come back, you're off a little bit, but you snap back in. That is a Kalman filter. It takes measurements from sensors, and in their absence or when they become noisy, it depends on a model. Each time step, it brings in a measurement from the gyro, the vision system, and says, this is my measurement. I run it through my model and see, this is my estimate of what I think reality should be. What was my guess from my last round? Compares the two, steps that forward, and repeats. I could go through this, but I think the freeway example probably made a better example. It should be noted that filters have an interesting property. They're generally two-frame. You take the last frame and you move it forward to the current frame. Then you repeat, just 2 frames at a time. March yourself forward. We'll see that there's another approach to solve this problem, something called a batch method as well. There are 2 ways of solving this problem. One's called tightly coupled, the other's called loosely coupled. The tightly coupled approach says, I'm going to take my camera and all of my features, hundreds or thousands, and my IMU, and put it into a big state estimation system. Add a new feature, add a new state. problem is Kalman filters build matrices, and I need to do a matrix inversion. Matrix inversions are order n squared, depending on how you want to argue it, order n cubed. That means as I double the number of states, I have 4 times the number of computations required. That's a heavy load. If I do a loosely coupled system, I just run my Kalman filter on the IMU, run that through, and then I'm only dealing with 22 states. And then separately run the pose estimator from the vision system. There's some merits to this. Tightly coupled solutions will give you a much more accurate solution at the cost of enormous computational load. Loosely coupled systems are not as accurate, but they're much faster. When I'm dealing with a small battery, that can be an important constraint. So here's an example from a paper from Weiss and Seagart, showing an example where they intentionally tricked the vision system about halfway through. The vision system was found, they moved some feature points, occluded them, and the vision system went off. But the inertial system held on to truth quite nicely. They were able to ignore the occlusions from the vision system, hold on to truth even in the absence of that, and then when the vision system comes back online, feed it back into the solution. This is what Kalman filters excel at. But there's other methods. A very popular one called bundle adjustment. Where that term came from, I don't quite know. But it basically says, let's not just take 2 frames, let's take hundreds. And then I can find a far more optimal solution. But if I'm going that far back, do I need to keep them all at 60 hertz? Maybe not. In fact, you can start to be quite intelligent about it and only take the ones that you need. For example, if I'm standing here and not moving, I'm probably not generating interesting keyframes. But when I start moving quickly, I probably want to chunk along a bunch of keyframes. Then I can do bundle adjustment on that, fit my position over time, and therefore get a more accurate solution. Part of the reason this is interesting is I'm no longer running my vision system at full 60 hertz rate. I'm only looking for interesting keyframes and then throwing that into a separate thread that runs in the background. This is a far more efficient system to do, and it's actually a lot more accurate because I'm only looking at interesting information, something with diversity to it. There's other information to provide. As we mentioned, consumer sensors, well, they're cheap and they're also noisy. We talked about that. But there's other information I can provide. With robots, I can identify whether or not I've actually sent a drive signal to the wheels. Am I moving? If I'm not, then I probably don't need to generate keyframes. With humans, it's a little bit harder. But I actually can use contextual analysis, contextual awareness to identify whether I'm moving, sitting, looking, what I'm doing. And I can feed this into these solutions to help constrain it. We saw that with the map of walking through the building. Now, that's a pedestrian dead reckoning solution. In that case, I've applied constraints to the problem. Here's an example from some of the work that we've done. This is kind of an interesting one. This is a fused vision PDR solution. Started walking at the pink dot, and you see the steps soon are identified. The vision system had a scale error, and it took it a while to get the right dimensionality. And you see at some point, the vision system was off. At some point, the scale factor was corrected, snapped to proper scale, and then was able to map to the PDR solution. Here's another example where we had occluded the vision system halfway through, and you can see at this point here, and you can see that even though we had a vision outage here, the PDR solution was able to hold on to its reference, properly follow, and then to continue on. Okay, I think I had one more there. Okay, similar examples. What we're basically arguing here is that fused solutions are more robust. I'd love to talk about SLAM, simultaneous location and mapping, as well as PTAM, parallel tracking and mapping. But I think I'm going to be followed by someone who knows this much better than I do, the gentleman from Google. So I'll let him talk about that. And he can tell you about, he probably actually did this, walked up and down that stairwell. I haven't. Let me just finish up by talking about other applications. Optical image stabilization, super resolution. This is an interesting example where there's intra-frame and inter-frame interpolation that allows you to up-resolve an image. If I take 3 or 4 images of the same picture, as done for this castle, each image, I can't hold it perfectly still. It's going to be slightly off just a little bit one from the next. And so I effectively have different pixels that have inter-pixel resolution. I actually have sub-pixel sampling of the space. So if I've got 3 images here, each slightly off, I can actually have several pixels. And I can now interpolate within those and gain super resolution, much beyond the capability of the actual imaging system. To do this, I need to know where those are, and I can aid that with an inertial system, or I can do that by proper fitting from doing alignment from within the vision system. Both can be done. And then there's deblurring. Deblurring is where I have blur within a frame. Since it's within the actual frame, I can't get visual information to help correct it. But if I do an inertial system to actually map the motion of the camera within the frame, I can deblur this. Adobe made quite a splash with their Adobe Photoshop deblur, where they actually started to do estimated solutions to see what was your deblur, solve it, and up-resolve the image after the fact without knowing. That's hard and computationally expensive. But if you bring in inertial information, attitude quaternion, I can actually track where I think the blur path was and de-blur and up-resolve the image. And there we are. I think I have 3 minutes left. Thank you very much.